So let's see another identity between binomial coefficients that may turn out to be very helpful, which is called Pascal's identity. And it says that n choose k minus 1 plus n choose k equal to n plus 1 choose k. So, written in this form, I would say that it is completely unenlightening. To me, this doesn't really look like anything. But let's talk about what you can use it for, and then also we will prove it, and hopefully with those things, it will start to become clear what is going on here. So, first of all, you will remember that we have talked about recursively defining sequences or defining numbers. And this is what you do when you define some numbers in terms of numbers that came before in the sequence. So if you look at Pascal's identity, you should see that it is a sort of recursive formula for binomial coefficients. Because it is telling you some kind of n plus 1 binomial coefficient in terms of some n binomial coefficients. So you can use this formula to basically iteratively compute bigger binomial coefficients. And so let's do some examples of that. It is convenient to write them in a triangle. And you may have heard of this, it's called Pascal's triangle. So basically, why we do this is because if we write them in a triangle like this, let's see. Then let's take a second to interpret Pascal's identity in this form. Why are we writing it like this? It's because these two people, adding up to this thing, we're displaying it graphically as the two top neighbors of each cell, adding up to the one below it. So for example, the things that I've circled is the case n equals 1 and k equals 1. So this is n choose k, this is n choose k minus 1, and this is n plus 1 choose k. And that's telling you that basically, let me erase all these marks, but this guy plus this guy equals this thing. Etc. So let's write some actual numbers. So 0 choose 0 is 1. There's one way to choose no things from a set of no things. That's kind of weird and vacuous, but let's just call it 1. And anything outside the triangle, right? We're saying that this is equal to this plus this. This thing you can consider to just be a 0 if it's outside the triangle. So starting with 1, we get 2 children here, which are both 1s, because we're going to add 0. And then continuing, we get 1, 2, which is the sum of these guys. 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. And the point of Pascal's triangle is basically just that it's a very useful way to visualize and work with binomial coefficients. So as a kind of an example, let's just verify this thing we proved a second ago, that the sum of all the binomial coefficients with a fixed n is 2 to the n. So if that was a bit abstract before, now we're essentially saying that if you add up the row, any row of Pascal's triangle, you get a power of 2. So this is 2 to the 0 is 1. 2 to the 1 is 2. Checks out. 1 plus 2 plus 1 is 4. That is 2 to the 2. 1 plus 3 plus 3 plus 1 is 6 plus 2 is 8. That is 2 to the 3. 1 plus, so this is 10, 15, 16. That's 2 to the 4. And etc. So basically, that is one of the uses of Pascal's triangle, is that a lot of the identities between binomial coefficients you can visualize really well using Pascal's triangle. For example, the rows add up to 2 to the n. You have Pascal's identity, which says that this thing plus this thing equals this thing. And there's loads more. But I want to leave it at that for now because I want to prove Pascal's identity. So we will give another combinatorial proof by interpreting, so let me rewrite it. It's n choose k minus 1 plus n choose k equals n plus 1 choose k. So we're going to interpret these as counting the same thing in two different ways. So the right-hand side, so let me say combinatorial proof. The right-hand side is counting ways to choose a subset of k elements from a set of n plus 1. Just a single binomial coefficient, pretty straightforward. The left-hand side so this is going to start to give us an idea of what kind of cleverness you can start to inject into combinatorial proofs, because we want to, excuse me, we want to reinterpret this in a way that makes it look like the left-hand side of this equation. So how can we do that? We have to, come up with some slightly different method for doing the same thing. So the left-hand side we can interpret like this. Choose an element of our set of n plus 1 elements, which leaves n other elements. So we've chosen some specified guy. There's nothing special about it. We're just choosing it as an auxiliary thing. So every k element subset let me call this element x, just so we have a name for it. So every element, every k element subset of our set of n plus 1 elements either contains x or not. So we can find the number of k element subsets by counting them in these two different categories. And notice that there is no overlap. You cannot both contain X and not. So these are going to be totally separate, and we will use a straightforward sum rule to add them together. So those containing X, how many subsets are these? Well, basically we have n elements remaining, and we want to choose k minus 1 of them, because we've chosen 1 already. And those not containing X, maybe you can see where this is going. Well, we have n elements remaining, and we want to choose k of them, because we do not contain X, so we need to choose k other elements. So the left-hand side, we have found, also counts k element subsets of a set of n plus 1 elements. And since these two sides are counting the same objects, that shows that they are equal, which completes the proof. So combinatorial proofs can become, the sky is the limit. There are much more complicated proofs than this, but this starts to give you an idea of, some amount of imagination was required to come up with a different way of choosing a subset that makes it look like this left-hand side. And here is, we can actually generalize this pretty immediately. So let's say generalization is called Vandermon's identity. And it says that n plus n, choose k. Or let me say n plus n, choose r, is equal to the sum from k equals 0 to r of m, choose r minus k, times n, choose k. And the proof of this, maybe I will give you a couple of seconds to look at this statement and look at this statement and see if you can imagine how the proof goes. Because the claim is that it uses the exact same idea. So I won't go through the proof in great detail. I will leave the details for you to work out if you are interested. But here's the idea. So in this proof of Pascal's identity, the right-hand side is choosing a subset from a set, and the left-hand side is fixing a specific element and considering subsets that you get by choosing that element or not, and choosing from the rest of the set. So this proof is exactly the same idea, except that we split our set of m plus n elements which is what's happening on this side, into a set of m and a set of n, which is what's happening on this side. And then how do we choose an R element subset from this set? Well, we choose R minus k elements from the first one, from this guy, that's this term, and k elements from the second. That's this guy. And then it's basically just, that's basically the whole idea. Then you just need to take the sum over all the different values of k, because you can take different amounts from each subset. So that completes our little proof sketch. And that completes our discussion of binomial coefficients and the many identities between them. Although maybe it's worth saying that there are many, many more identities than the ones we've talked about today. If you want to find out for yourself, my suspicion is that if you look up the Wikipedia page for binomial coefficients, I think it will be many pages long. Many, many pages of identities like these.